Some of you may have seen this on curriculum night, but I'm going to use the same bit because it's just too good not to use. 17 take away 9. Traditional algorithm says I always start in the ones column. And I always start right here. Or technically, I always start all the way to the right. It's not always a ones column. And I say I can't take 9 from 7, so I have to regroup. I have to borrow. That I can do. I can do that. I can do 17 take away 9. Thank goodness I've changed it from 17 take away 9 into this friendly problem. And this is what happens when kids become too accustomed to a robotic algorithm, that they crunch through the problem without thinking about it. And this is one where I'm gonna look at, I mean, there are lots of ways that I can ask kids to think about 17 minus 9. Whether you're counting up from the subtrahend to the minuend, whether you're counting up from the smaller number to the larger number in this case, or whether you're visualizing it, and we'll talk about this in a second, on an open number line. Open number lines are great tools if you're ever doing addition and subtraction, especially with your children, and you're stuck. An open number line, that is to say a number line without hash marks, lets kids really play with the stuff between it. I had a girl named Kazumi a couple years ago who said, I can look at any two numbers and I can find a really friendly number between them. And if I can find that friendly number, and I know the jumps on either side of it, I can turn any subtraction problem into an addition problem. That 17 minus 9 was the same as 7 plus 1. And that's the way she did every single subtraction problem. If it was a 12-digit problem, she didn't care. She'd find convenient numbers, landmark numbers, friendly numbers in the middle of it, and she'd count up. Takes about as much time as the algorithm. Makes a lot more sense when you look at it. Whereas what we've traditionally done, this is terrific. I'm just going to move this up a little bit so you're going to lose a little bit of text. I can't take 5 from 2, so I better borrow. Right? 2,730 12. Breaks every rule we've taught them when they were adding. We said, well, if it gets above 9, you have to carry into the next column because you can't have a 2-digit number in one column unless you're subtracting, and then you can. Now I can't take 8 from 3, so I better borrow again. So I have 2,613 d12, right? And I can't take 9 from 6, so I'm going to do that. And I have 1,1613 d12, which is 1,1613 d12. It's the right number, but look what we've done to it. We've mangled it. This doesn't make sense. Nobody can regroup in their head. Well, nobody I know can regroup. Maybe some people can do that in their head. And the traditional algorithm for regrouping, with addition, I said, with really large numbers, it has a place. I think with subtraction, it almost never does. I can't think of a time when this is the ideal way to subtract. And one of the tricks I came across in my wide math travels, a woman named Kathy Fosna, who started math in the city, talked about that numbers in a subtraction problem have a distance between them that remains constant. A difference between them, rather, that remains constant. And if I have these two numbers on a number line, and I move them up by a certain amount, in this case it could be an arbitrary amount, when I move them up, the difference between them stays constant. She called this constant difference. She didn't invent it. She popularized the strategy. She said, well, wait a minute, why would I do that? What if I can add something to both of these numbers that makes them friendlier? Like I know that my subtrahend, the number of my subtracted quantity, is 15 away from a really friendly number. So if I add 15 to this, and I want to keep the distance between them constant, I add 15 to both of them. The new problem becomes something anybody can do in their head. And to answer the same question from before, is this what I do when I look at this? This is exactly what I do when I look at this problem. It saves me from reaching for a pencil. So constant difference, I mean, if you can add a friendly number, you break the back of the... I'm going to use that all the time now. I'm going to be using that in class. I will quote you. I will cite you on that. But that is... It's spectacular. It's spectacular. This breaks the back of the problem. It becomes non-problematic. Right? So when we're talking about, when we're looking at subtraction, sure, I need kids to be able to solve, I need kids to be able to solve any problem. I need them to have a method that works. But that said, if the one method they have takes them 7 or 8 minutes, and a little bit of flexible number play will reduce the problem to this in 20 seconds, then by all means, flexible number play, right? All right.
Is this dependent on the children having the understanding that you were saying they were learning at Calhoun?
Absolutely. Well, is it dependent on that? It's dependent on flexibility. It's not dependent on Calhoun.
No, I mean, but a child who's going to be successful with this method has to understand regrouping very, very significantly. Is that?
Might not have to understand regrouping as a strategy, but might have to understand subtraction very significantly. Might have to understand, we do almost all of our subtraction work is with open number lines. And it's the kind of thing where we kind of tease out that idea. If you start with something where you're subtracting 1999, and it's only 1 away from a very friendly number, it's going to start bubbling up in the class. And wait a minute, there's something we can do here. This is not as easy as it could be. And there are lots of, again, hybridized strategies where you'll say, well, something's 1999, can't I pretend it's 2000 and then fix it at the end of the problem? And again, that's the kind of conversation we're looking for. If I hear that from a student, I'm going to ask another student to put it into their own words. Yeah.
Are you presenting subtraction vertically or horizontally?
Well, I'm going to be presenting subtraction in a context. For example, when we're looking at it with census data, it's always going to be, in 1790 at the first census, Delaware had so-and-so many people. How many more people does it have now? Because I don't want them to read, I mean, having this on a worksheet, I think does kids a disservice, because you're taking the sense of contextual math out of it, you're telling them what the problem requires, and that's a big part of math. Math isn't just the computation, it's also knowing what the scenario requires. So I try to do this as infrequently as possible. If I'm talking about formalizing constant difference as a technique, then maybe I would do that, but otherwise it's all going to be in context. It's all going to be in exploration. Did that make sense? All right, oh, here's my constant difference. Oh, see, I had a whole graphic all set up for it. See, why didn't I? So the distance between them remains the same when you move it up. Why do I set these things up for myself?
Can I say something in defense of the vertical form?
Sure.
The motivation for doing the vertical thing with 2 numbers that you're adding is that if you can do that, it lends itself very naturally to multiplication.
It does.
And
if
I don't see how you get from the horizontal thing to multiplication.
If the multiplication that you're doing is all vertical, sure. It certainly lends itself to the traditional algorithm for multiplication, but that's where we're going now.